Welcome back to my YouTube channel. Today we will discuss Rolle's theorem. Rolle's theorem is the most important theorem in real analysis. Okay. The statement of the Rolle's theorem is say that any function from closed interval ab to r with have three property. First property is f is a continuous on closed interval ab and f is differentiable on open interval ab and f of a equal to f of b. Then there exists C belongs to open interval AB such that f dash C is equal to 0. That is statement of the Rolle's theorem. Okay. First of all, explain in graphically of Rolle's theorems. Okay. Suppose this is my x-axis. Okay. And this is y-axis. And this is y-axis. Okay. Here the function have the three properties. Okay. Property number one, function is must be continuous on closed interval ab and function is differentiable on open interval ab and end point of the function is equal. That is, suppose this is my a and this is my b and end point are same. Suppose this is my point function value f of a here, okay, and this and f of b here. 2 points are same value. Okay, this is a comma f of b, f of a, this point, and this point b comma f of b. Okay, here given f of a equal to f of b and function is smooth because function is differentiable on open interval ab. So either function is straight line, okay, from here to here function is straight line. Suppose this is straight line, so straight line, this function value must be this f of a or f of b, okay, any value. So this implies function is constant. So we look every point on this straight line here, here, here. The slope of the graph is equal to 0. Okay, slope of the graph equal to 0 and tangent at the every point on this straight line is parallel to x-axis. Any tangent, okay, parallel to x-axis. So this implies slope of the tangent is equal to 0. In this case, every point value, we can find every point on open interval AB, f dash c equal to 0. Okay, in this case, if graph of the function is straight line. Or second case is possible, suppose function is not straight line, function of the graph is not straight line. So here end point is same. So any function from here, started from here, they must be bent at a time. Okay. So here the tangent at the point, tangent parallel to x-axis. This is my tangent at the point here is parallel to x-axis. So the slope of the tangent at the point is equal to 0. Okay, so here this point, corresponding point is my c. So here f dash c equal to 0. Okay, that means Rolle's theorem is guarantee that the c lies between a and b. This is Rolle's theorem, say that. Okay, so now this is my graphically view of the Rolle's theorems. Okay, now mathematically we can also prove. So now proof in mathematically. Given that f close interval a comma b to r is a continuous function on closed interval ab. Okay, by extreme value theorem, if is bounded and attained supremum and infimum, that is least upper bound and greatest lower bound. And this extreme value theorem we already discussed the previous lecture. Okay, so let b equal to supremum of f of x such that x belongs to a comma b. Okay, and b dash is equal to infimum of f of x such that x belongs to closed interval a comma b. Okay, and it is attained, so there exists c1 belongs to a comma b such that f of c1 is equal to b, and there also exists c2 belongs to a comma b such that f of c2 equal to b dash. Okay, this is called it equation 1. Okay, now here two cases arise. Either b equal to b dash, intimum and supremum of the graph of the function or range of the function is same, or b not equal to b dash. Okay, so case number 1, if b equal to b dash, okay, intimum and supremum of the function is same. Okay, so here we know that b dash less than equal to f of x less than equal to b for all x belongs to a comma b. So this implies here, this implies f of x equal to b or b dash. Okay, for all x belongs to a comma b. So this implies f is a constant. Okay, constant on a comma b. So this implies f dash x equal to 0 for all x belongs to a comma b. Okay, in this case here see every point of a comma b. Okay, so in this case the Rolle's theorem is proved. Now second case, if intimum supremum not equal to infimum, okay, b not equal to b dash, so at least one of b and b dash unequal or different. Okay, unequal to f of a and f of b. Okay, at least one of b and b dash unequal to f of a and f of b. Why? Suppose b and b dash is same as, both are same as f of a and f of b. If this is hold, so by the condition of third condition of the statement, here third condition is given here, this condition, third condition is given that f of a is equal to f of b. So we can find b equal to b dash, since f of a equal to f of b. So we already given b not equal to b dash, so which is a contradiction. Okay, which is a contradiction. So at least one of b and b dash unequal to f of a or f of b. Okay. Without loss of generality, suppose b not equal to f of a. Suppose b not equal to f of a. Okay. So from 1 this, okay, from 1 we can find f of c1 not equal to f of a. Okay, so this implies c1 not equal to a comma b. Okay, because f is a function is well defined. Okay, now this implies a less than c1 less than b, that is c belongs to open interval a comma b. Okay, c1 belongs to open interval a comma b. Okay, so given that, also given by second condition of this statement, f is differentiable on open interval a comma b, so this implies f dash c1 is exist. Okay, if f dash c not equal to 0, so here two conditions also arise. First condition, f dash c1 greater than 0, or second condition, f dash c2 is less than 0. Okay, now first case, f dash c1 greater than 0. Okay, so by definitions of the differentiability or derivative, this implies limit x tends to c1 f of x minus f of c1 by x minus c1, this is greater than 0 for all x belongs to a comma b. Okay, now so by the property of the differentiability or limit property, there exists del greater than 0 and for all x belongs to c1 to c1 plus del intersection a comma b, we have this quantity greater than 0, f of x minus f of c1 by x minus c1 greater than 0. Okay, we can always find an neighborhood, this condition is hold. Okay, greater than 0. Okay, now from this inequality we can have f of x minus f of c1 greater than 0, so this implies f of x greater than f of c1. Okay, but f of c1, this is my b supremum, so f of x greater than b for all x belongs to a comma b, which is a contradiction, because b is a supremum, b is a least upper bound of f. Okay, so this is a contradiction. B always less than equal to f of x always less than equal to b, because b is a LUB of f. Okay, here we consider x belongs to c1 comma c1 plus del. We not consider this point c1 to c1 minus del. Why? Because we choose x between c1 less than c1 minus del, so we always that these quantities x minus c1 is negative, so we can choose x minus c1 is positive, so we can choose here the neighborhood interval c1 comma c1 plus del. Only consider those of point, because of x minus c1 is always greater than 0. Okay, here now, so in this case we can find f of c1 not greater than 0. Okay, now second case. If f of c1 less than 0, okay, f of c1 less than 0, f dash c1 is less than 0. Okay, so by definition, limit x tends to c1 into f of x minus f of c1 by x minus c1 less than 0 for all x belongs to a comma b. Okay, so there exists del greater than 0 such that c1 minus del comma c1 intersection a comma b for all x belongs to this interval, we have f of x minus f of c1 by x minus c1 less than 0. Okay, here x lies between c1 and c1 minus del. Okay, so x less than c1 and c1 minus del, so this inequality given x minus c1 quantity is less than 0. Okay, so multiplying x minus c1 the negative quantity, so this inequality is opposite sign. Okay, so f of x minus f of c1 by x minus c1 greater than 0, so this implies f of x minus f of c1 greater than 0. Okay, so this implies f of x greater than f of c1. By similar case number 1, which is a contradiction, because this equal to b and b is a LUB of f. Okay, so in this case f dash c1 not equal to not less than 0. Okay, so this implies f of c1 equal to 0. Okay, and c1 must belongs to a comma b. From here, from this, so therefore here c1 is my c, which belongs to a comma b, such that f dash c is equal to 0, and Rolle's theorem is satisfied. and prove.